Hello class. So in this video, we're going to continue on section 4.7, L'Hopital's rule, right? So in the previous videos, we saw that we can use L'Hopital's rule for whenever we have an indeterminate form, which is either 0 over 0 or plus or minus infinity divided by plus or minus infinity. Right? We also saw that we can use L'Hopital's rule as many times as we want, as long as we get an indeterminate form, right? That's the condition that we need. Okay, so as of now, that's really all the things we're going to learn. Other than that, it's just working out limits. So I'm going to do another example. Now, in all the examples I did before, it was pretty easy to tell when we had an indeterminate form. Okay, so what's gonna make the problems a little bit harder? Well, when it's not as easy to tell, so you're gonna have to do a little bit of algebra to get there. Okay, so this is a good example of this, and we'll see more of these examples in the next videos. Okay? So suppose I want to find the limit as x approaches 0 from the right of sine of x times the square root of 1 minus x divided by x. Okay. Notice, this is a product of functions. If both limits existed, I could just evaluate, but plug in x equals 0 into both functions. Right? And when I say a product, I'm thinking of this is a function and this is a function. However, here we have a problem because if we look at this function here, I can't just plug in 0 because if I do, I'm dividing by x, which if I plug in 0, well, that's dividing by 0. And in the form it is now, this doesn't look as 0 over 0 because it's just a product. It's not even a quotient of functions. So this is actually an indeterminate form, but it's in disguise. You have to do a little bit of algebra first to simplify this and get it in a form that looks like 0 over 0 or infinity over infinity. Okay, so how am I going to do this? Well, I'm just going to simplify things a little bit. Again, no limits right now. I'm just going to do a little bit of algebra. So what I'm going to do is I'm going to divide this square root. If you remember, if you have the square root of a ratio, it's the same as the square root of the top divided by the square root of the bottom. So I'm going to write this as square root of 1 minus x divided by square root of x. Now, if you remember how fractions work, if you're dividing by something on the bottom, right, so like I'm doing here, I'm just dividing the square root of 1 minus x. But by properties of fractions, it doesn't matter in which order we do the division, meaning that this is the same as dividing everything by square root of x. Okay, so you see the small difference there, that here I had the square root of x only dividing this. Here, since the order in which you divide doesn't matter, I can just write it like this, where the square root of x is dividing actually everything. And now let's see what happens if we take the limit of the top divided by the limit of the bottom, because now we have a quotient. Now we can actually see if L'Hopital's rule applies. Okay, so if I do that, let's see what it looks like. So I take the limit as x approaches 0 from the right of sine of x times square root of 1 minus x divided by the limit as x approaches 0 from the right of square root of x. Okay. So what do I get? So now on the top, I have a product of functions. Both limits exist. So I can just take the product of the limits. I can just take the limit of this times the limit of this. That's the product property of limits. Okay. So sine of 0 from the right, that's still 0. Square root of 1 minus x from the right, that's x approaches 0 from the right, that's 1. So we get 0 times 1, that's 0 on the top. Limit as x approaches 0 from the right of square root of x is 0. And notice here that it matters that we're doing from the right, because for square root of x, we can't actually approach 0 from the left because the function doesn't even exist. Right? So it's important that it's the limit as x approaches 0 from the right. Okay. So what do we get? We get 0 over 0. That's an indeterminate. We can use L'Hopital's rule. Okay. So see, the only difference here in this problem was that it wasn't obvious that this was an indeterminate form. You had to use a little bit of algebra to simplify the expression first. And that's the idea. Sometimes expressions are not going to look like they're indeterminate, So you have to rewrite them in a clever way so that you get something that's actually a quotient that when you take the limits of each part separately, you get 0 over 0 or plus or minus infinity divided by plus or minus infinity. Okay, so let's finish up the problem. By L'Hopital's rule, then we can just find the limit as x approaches 0 from the right of what? So we take the derivative of the top and bottom. Right, so what do we get? So we need the derivative of sine x times square root of 1 minus x. So we have to use the product rule, right? Okay, so for the top, I'm going to use the product rule. Derivative of sine is cosine. Leave square root of 1 minus x the same. Remember, square root of 1 minus x is the same as 1 minus x to the 1 half, right? Plus, now I take the derivative of square root of 1 minus x, right? That's bring the 1 half down, leave the inside the same, multiply by that derivative of the inside. Well, the derivative of 1 minus x is minus 1. And then you leave sine the same. And that matches what we have, so that's the product rule. And on the bottom, we have the derivative of square root of x. Well, again, that's 1 half x to the negative 1 half. Okay. Now, we're going to simplify everything. So actually, since I'm just simplifying, I'm just going to write equals. And actually, here you can write equals, right? As long as you write it from the previous limit. So you can write that the first limit equals this second limit, right? That's fine. Here, since I switched pages, I want to write implies, just it's clear that we know what we're doing. Now, if we simplify, what do we get? Well, I'm actually just gonna do one thing here. So what am I gonna do? This x to the negative 1 half, I'm gonna make the exponent positive by moving it to the top. Okay, so I'm gonna get the limit as x approaches 0 from the right. I move the square root x to the 1 half to the top. So that's multiplying everything here. See here, I'm gonna simplify a little bit. I have a minus 1. I have 1 half minus x to the negative 1 half times sine of x. Now, this 2 here, so have a 1 half on the denominator. Remember that having a 1 half on the denominator, so if you're dividing by a fraction, it's the same as multiplying by the reciprocal. Right? So if I multiply instead by the reciprocal of 1 half, I'm just multiplying by 2. Okay. Now, if you look at this expression, I'm not dividing by anything, and every limit is defined. Right? If you look, if I take the limit as x approaches 0 of this, it exists. Of this, it exists. Of this, it exists. Same for here. Same for here. So the limit exists everywhere. I can just evaluate at 0 everywhere. Okay, so what is this going to be? Well, it's just going to be 0 because this limit is 0. So I don't really have to evaluate the rest. As long as I know that this limit exists, I can just say, okay, whatever that limit is times 0, that's 0. So what does that tell us? Well, the original limit, which was sine x times the square root of 1 minus x over x is just equal to 0. Okay. So again, the idea here is that it wasn't obvious that this was an indeterminate form, so you have to rewrite it a little bit. So in the next videos, we're going to see a couple of nice ways in which we can write things that don't look like indeterminates, but actually are, like in this example.